Recall in trigonometry for the circle of the radius r, we are going to find the area of the sector with an angle theta from the initial side to the terminal side. The area A is 1/2 times r squared times theta. This time we are going to find the areas of the regions bounded by the polar curve. For the polar curve, from an angle theta equals alpha to an angle theta equals beta as a polar curve, we use a slice in some technique. Each slice is the partial of the angle theta. So for each slice or each sector, the area is the area differential. We use the term dA is 1/2 r squared times the angle differential or the d theta. Now we're gonna sum or add all the segment areas together to form the areas of the regions bounded by the polar curve. So we have the formula A as a definite integral from alpha to beta 1/2 r squared d theta, where r is the function of theta. The area differential represents the difference of the areas from angle alpha to angle beta. For the case that we find the regions as a difference of the two polar curves, we have the longer radius r2 and the shorter radius r1, as both r1 and r2 the function of angle theta. The area or the difference of the area there is the definite integral of the 1/2, the difference of the longer radius squared and the shorter radius squared with respect to theta. The steps to find the area of the regions bounded by the polar curve, the hardest part is to determine the limit of integration. In the xy coordinate system, the limit of integration from the intersections of the two graphs. So in general, the steps. The first one suggests the region R whose area is to be determined. Next, draw an arbitrary radial line from the pole to the boundary curve R equals f theta. And then ask over what interval of values must vary in order for the radial line to sweep out the region R. The last step, from part 3 or the step 3, you can determine the lower and upper limit of integration. And recall the R is the function of an angle theta. You can use the graphing calculator or the web-based graphing calculator to determine the area of interest. Let's see an example. Number 1, find the area of the region in the plane enclosed by the cardioid goes with the function R equals 2 times the quantity 1 plus cosine theta as the graph provided. If you are not sure what the graph looks like, or you have to do it by hand, we can do it by using the graphing calculator. At this time, I'm showing you how to use the TI-84 or the TI calculator family. So make sure the mode of the calculator is in the polar coordinate mode for that option. And then go to the y equal button and type in the function r equals 2 times the quantity 1 plus the cosine of an angle theta and let's check the mode one more time. The mode is not in polar, so I have to make sure the mode is in the polar coordinate. So we are good now. Let's go back to the y. As you see the angle theta, it was x before, now it should be in theta, which is what we are looking for. And now we're gonna see the graph of this polar function. So we have the cardioid that looks the same as what you have on your notes. Now we're going to determine the limit of integration. Um, one thing that you can see, the graph that we obtained, it has symmetry about the x-axis. So for our convenience, we just look at the first half of the graph and then multiply by 2 for our convenience in calculation. Let's see how the first half happens. So let's try with the x min x max. So I'm going to go to the window, and the theta mean, let's start from the 0 or the 0 radian, and the theta max, this value is 6.28, that is the 2 pi. So let's put in um, the value pi, Let's go to the key, the second, and then the caret. So to put pi there, and the step, don't worry about the steps. The x min -10, +10, that's fine. So let's see how the graph looks like. So hit the graph. So that means we have just the upper half. So the upper half from 0 to pi. How about the trajectory? Just to make sure we have the right trajectory. Let's check again with the window. This time, let's see if we put the theta max as pi over 2. So click on the second, and then the caret to get pi and divide it by 2. Let's see what the portion of the graph going to be to ensure. Okay, so the trajectory is in the counterclockwise direction. Now we're going to go back to the window to get to the normal mode, which is 2 pi, theta max is 2 pi. And see the graph, we get the full polar curve. And then we're gonna set up the integral of the limit of integration. As we confirm with the graph, it starts from 0 to pi for the first half, and this one has symmetry with respect to the x, or reflecting as we verified before. So the order pair r theta reflected about the x-axis to get r comma negative theta. So this case verified to have the symmetry with respect to x. From the definite integral, from the lower limit 0 to 2 pi, 1/2 the r, which is 2 times 1 plus cosine theta, and then the quantity squared, since r squared as part of the integrand, multiplied by d theta. With respect to x, so that means the integral from 0 to 2 pi can be formed as twice multiplied by 1/2 of the region. So the 1/2, that means from 0 up until pi. So we can clean up this one to be twice integral from 0 to pi, and then multiply by, for the integrand is 1/2, multiplied by 4 times 1 plus cosine theta squared with respect to theta. We got the setup done. And next we're gonna work on simplifying the integrand before we find the antiderivative. 2 and 2 reduce, we still have the quantity, the 4, and then expand the power 2, which give us 1 plus 2 times cosine theta plus cosine squared theta with respect to theta. And next, we work on finding the antiderivative of each term. The first one, we call this is the antiderivative with respect to theta. We're gonna get the first term as theta, the second term as 2 times sine theta. And the last one is a little bit tricky because we have the power 2. If you recall the technique of integral, the integral of, I'm going to put a note on the side here, the integral of cosine squared theta with respect to theta, we're going to apply the formula, which is 1 plus cosine of double angle divided by 2 is one of the trig identity to represent the cosine sequence. Now we have in this form, then we can find the antiderivative, which is theta plus 1/2 times sine of 2 theta. On the side here, we got the last piece done and put them all together to have 1/2 theta plus 1 over 4 sine of 2 theta. Evaluate from 0 to pi. And next, we just simplify the antiderivatives we just got. We see 0 and 1/2 theta. Not theta, sorry. It's theta and 1/2 theta. That combined to be 3 over 2 times theta plus 2 times sine theta plus 1 over 4 times sine of 2 theta. Evaluate from 0 to pi. And we can treat them like we can multiply all by 4 to avoid dealing with the fraction term. So let's go ahead and do that. 4 times 3 over 2 to be 6, so 6 theta plus 8 times sine theta plus sine of 2 theta. Evaluate from 0 to pi. Replace the theta with the pi or the upper limit. We get 6 pi plus 8 times sine pi plus sine of 2 pi, and then subtracted by 6 times 0, the 0, plus 8 times sine at 0, plus sine of 0. Sine 0 is gone, sine 2 pi is gone, sine pi is gone, so the answer is 6 pi.